This video tries to answer the question, what can the slope of a tangent actually measure? And in order to do that, we're going to revisit a concept from a previous video. On this graph that you see here, notice the x-axis is measuring time in seconds, y-axis is measuring height in feet. We have a tangent to a curve, and this is a previous projectile model. And what we know is that through local linearity, the slope of the tangent and the slope of the curve are the exact same number at the point of tangency. Again, it's called local linearity. And so for our purposes, let's say that this slope is equal to 20. We refer to this number of 20, or rather negative 20, as being the instantaneous velocity at this given time. And what that essentially says is the speed that the projectile would be falling. So what I want to address is what else can it do? So why don't we make a quick change here and think of maybe being in a chemistry class instead of a physics classroom. Notice I kept the slope the same, it's still negative 20, but what I did is on the x-axis, I left this as time in seconds, but I changed the dependent variable to temperature in degrees Celsius. So let's say you're doing some type of experiment in which you heated something and then let it cool. And I want to interpret what the slope means in this situation. So because of slope measuring change in y and change in x, I'm simply going to think of this as a replacement. And I'm going to replace the letter y, or the dependent variable, with just temperature. And then change in temperature over change in time. So in order to do that, I really kind of need two numbers. So I'm going to, instead of calling this negative 20, I'm going to call it negative 20 over 1. So here's how we would interpret this. Negative 20, I want you to think of the temperature going down 20 degrees Celsius. And then think of this as 1 second. So at that particular moment in time, the temperature is dropping 20 degrees per second. As an example of how you could use this in economics, notice that in this particular graph, the graph has changed. It's a different shape, but I still have a point of tangency on there. I have units produced and cost in dollars. So this would be measuring how much it would cost you to actually produce something new. So you came up with a new product, you wanted to take it to market, and you wanted to do a cost analysis. So if the slope of the tangent is 17, the slope of the curve is 17. So since our variables in this case are cost in dollars, so we're essentially looking at change in cost over change in the number of units produced. So in this situation, if the number is 17, think of that like positive 17 over 1. This is essentially cost in dollars, and then this is the number of units produced. So what this means is at this specific moment in time, the cost is increasing $17 per unit. And how the cost is changing, this measure of 17, and you will later learn this here, we call this marginal cost, or change in cost. And what that'll help us do a little bit later in the year is determine if are we producing the appropriate amount of units to keep our average cost down as low as possible. But we'll see that a little bit later on in the year. The moral of the story is this: anytime that you have any two independent variables and you find the slope of the tangent, what will happen is you're going to find what I'm going to call an instantaneous rate of change. An instantaneous rate of change is at a specific point in time. Now before, you could only do what was called an average rate of change because you needed the slope formula, and the slope formula needed 2 points, which makes a secant. And we don't want average anymore, we want instant, and that's where calculus comes in.